Welcome to the 10th lecture of EE311. In this lecture, we will continue on single transistor bipolar amplifiers. But before starting the lecture, I want to correct two things from the previous lecture. The first thing is that on slide 45, when we are having this DC equivalent circuit, when we are applying the Thevenin equivalent for the base voltage in here, there's a small mistake in here in the notes, so we have to correct it. The mistake is here. This expression is not correct. It should be, of course, VDD over R1 plus R2 times R2. So please correct it. So this is not correct, but I'm sure that you find it. And there was one more thing to be corrected. When we were finding GM, the transconductance of the bipolar transistor, we wrote this expression by definition, and then when we were taking this derivative, we wrote the expression for IC with a small mistake, so the correction is in here. So IC is ICS exponential VBE divided by VT. So we don't need this -1 term in here, and then the equation will be correct. And these corrections are mainly because one of your friends sent me an email and asked about these equations. I want to thank to him for his careful watching of the videos. Okay, anyway, in the previous lectures, in fact, we were dealing with the single transistor amplifiers, and we have seen three types of the MOSFET amplifiers. Then we started the bipolar transistors, and we solved common emitter and, of course, common emitter with degeneration. Now, today, we will deal with this common collector and common base amplifiers. For common base amplifier, you can see different schematics, of course, but they are the same, basically. On the left, this is mostly like, book type schematic for common base amplifier. Base is grounded, and the current is supplied with a constant current source, ideal current source. And you can find R in and R out in here. But a more realistic approach is using 4 resistor biasing. In fact, in this case, what happens in here, you can have DC bias at the base by having such a network. But in that case, of course, you have to put some isolation capacitor so that base is grounded AC wise. So these two circuits are equivalent to each other. In one of them, we have the biasing, in the other one, biasing, DC biasing for the base. For the other one, you don't need to do that because both DC and AC are grounded. So when we are dealing with such an amplifier, you can use a more realistic one if you wish, and you can work on this version. Let me draw in a clear page. Instead of the ideal current source, you can use 4 resistor biasing. You will find the same result. Expressions may be a bit different, but eventually the solutions will be quite similar. So this is a circuit. Instead of the ideal current source, you can use this R4 And in that case, when you are dealing with the DC circuit, DC equivalent circuit, you end up with the same circuit that we have used for common emitter amplifier. All these three circuits will work with the same. The first thing that you should do, of course, DC analysis. Verify that transistor Q is in forward active region, and then find the small signal parameters. The next thing, of course, small signal analysis. You have to replace the transistor with the either hybrid pi or T model, T small signal model, and short all the bypass and isolation capacitors and get rid of all the DC sources. So if you do that for this circuit, now I'm working on this circuit. If you do that for this circuit, sorry, I am using this circuit. Okay, so we are solving this circuit. If you draw the T model, please note that R1 and R2 are gone. Why? Because this is AC-wise ground. This is ground. No current passes through here. So this is gone. Shorted. The same thing for this one. It is shorted. Or in this circuit, you can see the same thing. This node is grounded. This node is grounded. This node is grounded. So you don't need to show R1 and R2. So in the T model, R1 and R2 are gone. And please use these node names all the time. It's going to help you a lot. And of course, we have to put the output resistance in here. Let me draw it with a different color. So there is R4, R0 in here. But remember that for RIN and AV calculation, you can ignore R0 if it is problematic. So R0 can be ignored in RIN and AV calculation. So we don't need to use it, so we can erase it from here. Okay. RIN, for finding RIN, you have to exclude RS, of course. You are looking from here. And when you take a look at it, of course, R4 appears in parallel with RE. If you are worried about using reflection or not, then it helps to show the currents on the branches. This is IB, this is beta IB, this is of course beta plus 1 IB, and as you see, small RE is on the beta plus 1 IB branch, which means that it's at the emitter branch. So you don't need to use reflection when you're looking from here. It's already at the emitter. If it was a hybrid pi model like this one, when you are looking from here, the current on this branch is IB. So as you see, our pi is not at the emitter, it's at the base. It's having the base current. So in this case, you have to use reflection, and you have to reflect this R pi to emitter somewhere in here by dividing the value by beta plus 1. So these two circuits are exactly the same, but let's show it in here. So when you take a look at from here, you have I base current, beta plus 1 I base current passing through here. So when you are looking from here, R pi is at the base because it sees IB current. Therefore, you have to reflect it. And when you reflect it, you are going to divide it by beta plus 1, and you will end up with small RE anyway. In the T model, this RE is already at the emitter node because it sees beta plus 1 I base current. So you don't need to use reflection. it was not here, it is here. So you can find Rin as directly equal to Re in parallel with R4, and this result is consistent with the hybrid pi model. When you take a look at from here, it's going to be R4 in parallel with R pi divided by beta plus 1, which will be exactly the same thing. So this is also equal to R pi divided by beta plus 1 in parallel with R4. And in fact, this resistance is low. Keep in mind that Re is something in the range of 1 over Gm, and this thing is generally like 25, 50 or something like that ohm. So 10 ohm to 50 ohm, let's say. So it's a low resistance. So input resistance is low, which means that you can use it for current amplification, because at the very beginning of the lectures I told you that for current amplifiers, when the input is current, you want low input impedance because you want to transfer all the current to your amplifier, so it can be used as a current amplifier. Not only as a current amplifier, you can use this thing like for trans resistance amplifiers. Why? For trans resistance amplifiers, input is current. When the input is current, you prefer low input resistance. So let's find the gain, the next thing. V out can be written as minus Gm R3 in parallel with RL, because this is Gm VBE, so I have to multiply this thing by VBE as well. So the current is Gm VB, it's going in the reverse direction. It's creating this V output voltage across R3 and RL. So I can write V out with this expression. Now I need to find VBE. VB is the voltage here. Okay. And VBE is in fact equal to VB minus VE. VB is 0. VE is the voltage in here, which you can find as a resistive voltage division between RS and Rin. So let's write it down. VBE is equal to VB minus VE, which is VE. This is 0 minus VE, which is minus Rin divided by Rin plus RS V signal. But please note that you have another negative sign in here. So eventually this will be, I make a mistake. No, so this should be negative. So therefore AV will be, let's write it in here. AV will be Rin divided by Rin plus RS times Gm R3 RL. So this is the final expression. And when you take a look at this expression, the important things are, this is positive, which means that input and output are at the same phase, no phase difference. So this is non-inverting. The other thing is AV of CE is equal to AV of CB. Of course, expression-wise. Please check the expression for AV of CE, common emitter amplifier gain. The only difference is this negative sign. Other than that, expressions are exactly the same, but there is one major difference. Rin is very low in common base amplifier. Because of that, this term is generally low. So for typical RS values, I said that Rin is set by this RPi divided by beta plus 1, or small Re, which is very low, which means that this term is much smaller than RS for typical source resistances, and therefore you cannot have large gain by using common base amplifier. Most of the time this gain is very low because of low input resistance. And because of that, people generally use this amplifier for current amplification. When the input is current, since the input resistance is low, most of the current is going through the amplifier and it's going to be transferred to the output. You can make a very good trans resistance amplifier or very good current amplifier by using this common base amplifier. So we find Rin, we find AV. It is quite similar to common gate amplifier. The last thing is finding the output resistance, and for the output resistance, using hybrid pi model can be more convenient. So let's use it. For output calculation, for ROUT calculation, what you need to do is kill independent sources and apply Vx, then find Vx over Ix. So this is what we have done in here. This V signal is shorted, it's killed. This is, by the way, RS, not R5. This is RS. So V signal is killed. A Vx potential is applied. Ix is defined, and I need to find Ix divided by Vx. Again, you can make a simplification in here. You can say that Rout is in R3 in parallel with our collector, let's say, where our collector is Vx over Ix prime. This is the Ix prime current. So we can write Vx is equal to R0 times Ix prime minus GMV pi. So the current passing through R0 is defined as this current minus this current. And Ix prime is in fact the current passing through here as well. And when you multiply all these three parallel resistances by Ix prime, you are going to find this potential, which is minus V pi, which is V emitter. And it will be like this thing plus Rs R4 R pi times Ix prime. Please note that I didn't use reflection in here. That is one of the most critical things. You should treat such a circuit like a regular circuit from 201. I mean, you don't need to use reflection. Why? Because reflection effect is hidden inside this dependent current source. You already take it into account with this term. Reflection is used only when you are looking from base or when you are looking from emitter. If you are looking from collector, since R0 is included and GMV pi is still there, you shouldn't use reflection. Okay, so this R pi should appear as it is in this parallel combination. That's one of the most critical things that you should be careful. So now I know V pi as well. V pi is equal to minus Ix prime R4 Rs in parallel with R pi. So Vx divided by Ix prime R0 1 plus Gm R5 R4 R pi plus Rs R4 R pi. And note that this thing is R0 times 1 plus something, and this thing is definitely larger than R0. But this thing is like, typical discrete components. The resistance value is maybe at most a few kilo ohms. This thing is like a few hundred kilo ohms. So this thing can be neglected. So you may not need to include this extra term in here. Now I know our collector. So from here, you should write R out as R3 in parallel with R0 1 plus Gm R5 R4 in parallel with R pi. Here there's something interesting in here, which may not be that critical for 311, but for your future courses. This parallel combination can be at most like R pi. So this term can be at most Gm times R pi. Gm times R pi is beta. So this part, the maximum value of this expression will be beta plus 1 R0. So the output resistance of the transistor itself, the resistance seen from here, let's say, or seen from here, sorry, can be at most like beta plus 1 R0. As I said, it's not in the scope of 311, but it's good to think about these expressions and their limitations. And this limitation tells me that whatever I put in here, the maximum impedance that I can get from here is beta plus 1 R0. That's the maximum output resistance of a transistor when you have some resistor at the emitter. Okay, so we find both R out, AV, and R in for common base amplifier. The last single transistor amplifier is common collector. And this is the schematic which is given in the book. Again, we are using a constant current source, but we are going to analyze a more realistic one, which is this one. We are using 4 resistor biasing again. C1, C2, and C3 are isolation or bypass capacitors, of course. R1, R2, R3, and R4. And you got the output from the collector part. So don't forget to name the nodes. Collector is here, base, emitter. Input is applied from the base. You got the output from emitter. This is named as common collector because collector is AC wise grounded, like in this one. This is AC wise grounded as well. Again, we are seeking for 3 important parameters for this circuit, which is R in, R out, and AV. R in is defined as the resistance seen from here, excluding Rs. R out is the resistance seen from here, which is given in here. So when you take a look at such a circuit without even drawing the small signal model, you should be able to tell some of these parameters. So R in, it's quite obvious, I guess, right? It's going to be, when you take a look at from here, R1 in parallel with R2 and in parallel you have this resistance. In that case, you can use reflection, of course. It's going to be R pi, the base emitter resistance of the transistor, plus these two reflected to the base, which is beta plus 1, R4 in parallel with RL. So please try to see it by yourself without drawing the small signal model, but I'm going to solve it by the small signal model. So this is the circuit with T model. So this is small signal T model. Of course, keep in mind that the first thing that you should do is DC analysis. Verify that transistor is in forward active, and then find the small signal parameters, which are GM and RE and R pi if required. So for Rin, that is the resistance seen from here. For Rout, it is the resistance seen from here. And R0 is not problematic. One end is already grounded. So what I can do is, I can just relocate R0 like this. It's not going to change anything. So this is much more easier for analysis. And I'm not ignoring R0 at any part of the analysis because it's not problematic at all. And keep in mind that putting node names will help you most of the time. So put them. Rin, the resistance seen from here, R1 in parallel with R2 in parallel with something like this. So writing currents in here will help you for the reflection. So it looks like that, in some cases you may not use reflection for all of them, but if you put the current values, this will help you a lot. So the current passing through here is beta I base. The current passing through here is beta plus 1 I base. So you have I base in here, beta plus 1 I base in here, which means that you have to reflect this whole impedance to the base for the calculation, which means that Rin will be equal to R1 in parallel with R2 in parallel with beta plus 1 times Re plus R4 R0 RL. And beta plus 1 times Re is of course R pi. Even if you use the hybrid pi model, you should end up with the same result then. For the gain is a bit more easier, I guess. So let's clear up this part a bit. So for the gain, we have two resistive voltage division. One is in here. So you can divide the gain as AV is equal to V out divided by V signal, let's say, which is equal to V out divided by VB times VB divided by V signal. For VB divided by V signal, you have the first resistive voltage division in here, which is Rin divided by Rin plus Rs. So you find VB in terms of V signal. For this one, V out and VB is the potential in here, V out is the potential in here. You have another resistive voltage division. So you just put the expressions for the resistances, and the result will be Rin divided by Rin plus Rs times R4 R0 RL divided by Re plus R4 R0 RL. So this will be AV. Important things about this expression is, first, it is non-inverting, of course. no phase difference between input and output. The other thing is it is less than 1 because this term is less than 1, this term is less than 1, so AV is less than 1. But while designing such an amplifier, you want to make the gain as close as possible to 1. You want to make it as high as possible. So for that purpose, what would you do is you are going to choose Rin as large as possible compared to Rs. You want to make Re negligible compared to these terms. So you use large R4 resistance and try to minimize Re. And this discussion is quite similar to common drain amplifier or source follower amplifier. In source follower, instead of this RE, we had 1 over GM, and 1 over GM and RE are almost equivalent to each other. So you are going to play with this RE to make amplifier gain close to 1, or of course you want to make this thing as large as possible compared to RE. The last thing is finding the output impedance, the resistance seen from here. And for finding this resistance, I'm going to use the same algorithm, the same thing that we have done over and over. For Rout, kill independent sources, apply Vx. So this is shorted. I should exclude RL, of course. Instead of Vout, I put Vx in here. And I try to find Ix passing through it. In fact, you don't need to make this calculation because you can use reflection. So this current passing through here is beta plus 1 I base. So you can reflect this resistance to the emitter and put it in here. And then you find the resistance seen in here. The next thing is you take it in parallel with R0 and R4. So if you do that, Rout is equal to R0 in parallel with R4. This is the easiest part. In parallel with Re plus the resistance at the base reflected to the emitter. Resistance at the base is Rs, R1, R2. When you reflect them to the emitter, base beta plus 1. So this will be the final expression. And Rout is, in fact, a low resistance because this value is low. These are a few kilo ohms, but it's divided by beta plus 1. So in total, this term is in the range of, let's say, a couple of hundred ohms, maybe. And therefore, it's going to be the limiting factor for the output resistance. And Rout is low. So common collector or emitter follower is a good voltage buffer. So to summarize, let's go back to this amplifier types and let's summarize their function. Common source, good voltage amplifier. Rin is large, Rout is large, AV is large. When you use degeneration, again it's a good voltage amplifier. But AV is a bit decreased. So if I put like one arrow in here, I should put 2 arrows in here. AV of common source is larger than AV of common source with degeneration. And in general, output resistance is improved by the degeneration. Output resistance of the transistor is improved by the degeneration. Input resistance of the transistor is improved by degeneration. For MOSFET, you don't observe it because the input impedance is already infinite and you don't see that. Common drain. Common drain is a voltage buffer. Rin is large, Rout is low, AV is less than 1, but you want to make as close as possible to 1 for a good design. Common gate, current buffer, gain expression is exactly the same with the common source, but the main problem is your input is low, so Rin is low, Rout high, AV low. You don't want to use it like a voltage gain amplifier, but AI is almost 1. And all this discussion is valid for bipolar cases as well. So you can say that all these discussions are the same for bipolar versions of them. Common emitter and common source are analogous. Common drain, common collector, quite similar. Common base, common gate can be replaceable. But of course, using a MOSFET and bipolar transistor makes some difference. For MOSFET, input impedance is very high because your transistor's input impedance is infinite. So you don't need to worry about gate current. Gate current is always 0. So setting Rin high is much more easier for MOSFET amplifiers. On the other hand, bipolar transistors GM value is typically for the same bias values, typically much larger than GM of MOSFET transistors. Therefore, you can achieve larger gains, larger GM values by bipolar transistors. So that's the beauty of using bipolar transistor amplifiers. And depending on the application, of course, you have to choose the proper one. But in an integrated circuit approach, for integrated circuits, generally MOSFETs are used because in standard CMOS fabrication processes, designing bipolar transistors or using bipolar transistors is quite difficult. Having MOSFETs are much more easier. So on ICs, you generally see MOSFET amplifiers, but if you are doing in discrete domain, you can see both of them. So let's stop in here. And then in the next lecture, we will continue with the small signal condition for bipolar transistors.